All right, let's go over some questions from exam 3B. First one, free response 1A. Build an argument using energetic factors to justify the weak acidity of proton A compared to proton B. All right, so the idea here is in proton A, when you generate the charge, it will be generated on this oxygen over here. In proton B, if you remove proton B, the negative charge will be over here. Okay, you see that the negative charge in B is one bond away from a double bond, meaning it can participate in delocalization of charge. Okay, because of that, due to feature 2, it's going to be more stable. Okay, if you have resonance stabilization due to delocalization of charge, it's going to be more stable. And then in option A, we don't have that opportunity for the delocalization because the double bond is 2 bonds away from the double bond from the negative charge. As a result of that, there's no delocalization of charge in proton A, which makes the conjugate base of that anion of that acid less stable. Therefore, it's going to have a lesser acidity. Okay. Now, we need to justify it here. Your justification should describe relative changes in the energy of electrons. Okay. So the proton B removal of, okay, let's say removal, let's say conjugate base, right? Okay, let's do that. The conjugate base of B is more stable, due to the delocalization of electrons, due to the delocalization of electrons. Right? Delocalized electrons, have more space between them, that reduces the repulsions between them. Therefore, the potential energy is lower. Therefore, the potential energy is lower. Okay, so that's why this is the energetic argument of why conjugate base of proton B is more stable. And then the entropic argument would be delocalization of electrons, delocalized charge in negative charge in B conjugate base, delocalization of negative charge in B reduces the charge density of the iron. Okay, ions with lower charge densities have less solvent organizing effect. Less solvent organizing effect. Therefore, the relative number of configurations will be higher. Therefore, the relative number of configurations will be greater. Okay, so the idea is in both cases when you have ions have solvent organizing effect, which reduces the number of configurations. However, because the charge is delocalized in B, in words, the same negative charge is spread out between 3 atoms in B. As a result of that, it's going to have a lower charge density, and that is going to have a lesser solvent organizing effect, and therefore the decrease of number of configurations is less in B compared to A, where the charge is more localized. Okay, that's why the relative number of configurations is greater in the conjugate base of B, when the conjugate base of B is in water, rather than the conjugate base of A is in water. Okay, which makes the acidity of proton B greater. All right, moving on, write the reaction of CBr3NH2 with water. Okay, let's do that first. CBr3NH2 aqueous with H2O would give us CBr3NH2 is an amine, therefore it's a base, and therefore we're going to have CBr3NH3 plus, because bases grab a proton from water, plus it's going to generate OH minus ions, OH minus AQ. Okay, this should be reaction of this molecule with water. And if you write the equilibrium constant expression for this, it's going to look like we're going to have products, which is CBr3 and H3 plus and OH minus divided by CBr3 and H2, which is our reactant. Products over reactants. And because we're talking about base dissociation, because this is a base reaction with water, this is also called the case of B, or the base dissociation constant. If the pH of 0.1 molar solution of this molecule is 10.2, what is the value of the equilibrium constant? You're given the pH. We know the pH plus pOH is equal to 14. Therefore, pOH is equal to 14 minus 10.2, which is going to be 3.8. Okay, so that's the pOH. And then we know for weak bases that, okay, if the pOH is 3.8, that means OH minus concentration is 10 to the power of minus 3.8 molar. Okay, and we know for weak bases, OH minus concentration is C0 times Kb, square root of that. Okay, so if you plug and chuck the values, 0.1 molar means 10 to the power of minus 1 is the initial concentration, times Kb is 10 to the power of minus 3.8, and the square root of this will be no, give me a second. So it's not the KB, it's the POH, which is 3.8. So we need to write that. This is not known. We are asking for the KB, equilibrium constant. So the K sub B, K sub B square root. Okay, so initial concentration times the K times K sub B or KB, and then the square root of that should be equal to OH minus concentration, which is 10 to the power of minus 3.8. Okay, and then we can rewrite this. I'm gonna square both sides. 10 to the power of minus 1 times K sub B is equal to 10 to the power of minus 3.8 times 2 is 7.6 minus 7.6, and therefore K sub B is equal to 10 to the power of minus 7.6 divided by 10 to the power of minus 1, which is 10 to the power of minus 6.6. And then that should be the value of equilibrium constant. If you want to, you can convert this to scientific notation as well. 10 to the power of minus 6.6. Right. Minus 6.6 is 2.5 1 times 10 to the power of minus 7. Okay. All right, so we have the K sub B now, which is the equilibrium constant value for this reaction. Okay, moving on. Free response question 3. The claim is valid. So now, okay, now we are given a drug. You are given the pKa values for each group over here. Right? Claimed that the net charge of this peptide is 0 in a solution where the pH is 3.9. So let's evaluate this claim. All right. So this is my group 1, group 2, and group 3. Okay, so let's think about the group 1. The pH is 3.9. It's easy to see that now. Okay, now with respect to group 1, pH is less than the pKa. Okay, therefore the acid form is dominant. Acid is dominant, and therefore we're gonna have this form. This is going to be the dominant form, dominant structure. Okay, and the charge here is 0. Okay, 0. And then moving on to group 2, pH, which is 3.9, is less than the pKa. Okay, therefore the acid is dominant. Okay, and the acid form of that group is NH3 plus. Okay, charge there is +1. And lastly, the third group, we have the carboxylic acid group. Okay, in the carboxylic acid group, we see that our pH is 3.9. pH is greater than the pKa. Okay, therefore the base is dominant. Okay, and the base form of the carboxylic acid group is COO minus, and then the charge here is -1. Okay, and therefore the net charge is the sum of all these changes. 0 plus 1 plus minus 1 is going to be 0. Okay, so yes, the claim is valid. Okay, moving on to question 4. Predict how the above chemical equilibrium will shift to products or reactants when water is removed from the solution by evaporation. Okay, you're evaporating water. Build a kinetic argument based on the effect of the perturbation on the rate of the forward and the backward processes to justify your prediction. Okay, so now if you consider the perturbation here, the evaporation, the perturbation causes the concentrations to go up, aqueous concentrations go up. Okay, due to perturbation, due to the perturbation, okay, due to the perturbation, C9H20 NO3, oh my god, S plus concentration increases, C9H19 NO3S concentration increases, and H3O plus concentration increases. Okay, so if you evaporate water, the concentrations go up because you're decreasing the volume, here. All right, anyway, now the question is how that is going to affect the forward and the reverse rates. So we know the rate forward is rate constant for the forward reaction times C9H20 NO3 is plus concentration, and then the rate for the reverse reaction or the backward reaction is rate constant for the backward process times C9H19 NO3S concentration times H3O plus concentration. Okay, we know that this concentration goes up. Okay, so both forward and the reverse rates are going to increase, but because you have two things increasing in the reverse rate or the backward rate, the increase of the reverse rate is going to be greater than the increase of the forward rate. Okay, increase of rate B is going to be greater. So as a result of that, rate B or rate reverse is going to be greater than the rate forward. Okay, therefore more reactants are formed until rate forward becomes rate backward again. Okay, therefore the reaction shifts to reactants. All right, so that's going to be the effect of perturbation, the equilibrium shift. Okay, now moving on to question 4b, how predict the effect of the above perturbation on the pH of the solution. Now we see that due to the perturbation, okay, due to perturbation, due to the perturbation, due to the perturbation, H2O plus concentration increases, right? Which means the pH must decrease. Okay, the reason is perturbation is always greater than is greater than the shift. Okay, even though the shift should reduce the H2O plus from the system to make more reactants, the initial increase of H2O plus concentration is much larger compared to the decrease of H2O plus concentration due to the shift. That's the idea there. All right, moving on to the last question. You are given the pKa of a certain compound, which is used to prepare buffer solutions. When you say buffer, you know that the equation that comes to our mind is pKa is equal to pH minus log A minus concentration over HA concentration, the Henderson-Hasselbalch equation. So in this case, our acid is this. This is our weak acid in this equation. And then this is our conjugate base. Okay, so we need to identify those now. Okay, and then if you rearrange this, we see that log base over acid. We can actually say base over acid at this point. A log base concentration over acid concentration is pH minus pKa. Yeah. Okay. And therefore, base concentration over acid concentration is 10 to the power of pH minus pKa, which is 10 to the power of 10.90 minus 10.43. Okay, and that is equal to 10 to the power of 0.47. Yeah, so 10 to the power of 0.47 is 10 to the power of 0.47 is around 3. Okay, so that means the acid concentration, base over acid concentration is 3. Therefore, the acid concentration is equal to base concentration divided by 3, which is going to be 0.6 divided by 3 molar, which is going to be 0.2 molar. All right, so yeah, those are the answers to the response questions. Actually, all of the pre-response questions in exam 3B. All right, I'll see you guys in class. Bye, everybody.